Robotik in der Industrie. Der Podcast mit Helmut Schmidt und Robert Weber. Hallo und willkommen zu einer neuen Folge unseres Podcasts Robotik in der Industrie. Mein Name ist Robert Weber und in dieser Folge geht alles ums Schweißen und die Robotik. Wir haben uns von den Kollegen vom AI eine Folge ausgeliehen, und zwar eine Welding-Folge mit den Kollegen von Path Robotics aus den USA. Die Kollegen haben ziemlich viel Kohle eingesammelt in den letzten Monaten und haben ein Welding-Model, ein AI-Welding-Model gebaut. Was das kann, wie das funktioniert, hört ihr in dieser Ausgabe. Viel Spaß beim Zuhören. Ciao. Well, hello everybody and welcome to a new episode of our Industrial AI podcast. My name is Robert Weber and my guest today is Andy from the USA, one of the founders of Path Robotics. Welcome to the podcast.
Hey, thank you guys so much. Really excited to be here.
Yeah, you are welcome. Please, Andy, before we start, please introduce yourself briefly to the listeners.
Of course. Yeah, I'm Andy. I'm the co-founder and CEO of Path Robotics. Started this company while I was doing my PhD. My PhD focused on deep reinforcement learning for humanoid robotics and worked on that about 10 years ago.
And you are based in Ohio, right?
Yeah, we're based in Columbus, Ohio.
So it's not West Coast or something trending. It's the mainland.
Yeah, we're in the heartland.
Yeah.
We wanted to be really close to our customer base and about most manufacturing, it really gets done in the middle of the country.
Okay. You have raised a lot of money in the last months, 100 million in Series D. What do the investors see?
Yeah, so we have raised a lot of money. A lot of that money is continuing to go to our R&D efforts. What we think about and what our investors think about a lot is how do we continue to build this AI? How do we continue to build this physical intelligence for manufacturing? It's still a massive gap in the market right now. You really have two dichotomies. You've got traditional robotics that are using PLCs and hand programming, and then you've got academics that are really just focusing on pushing the bleeding edge of technology. We'd like to sit in between, where we're really utilizing that capital to push the bleeding edge, but do it with what's actually been out for the past couple of years so that we can really start to see changes and growth in these models so that we can see these changes in growth for our customers.
So, but you focus the welding market, right?
Yeah, today we are focused on welding. So most of our customers, they do a lot of heavy deposition welding. There's three major verticals for us. There's energy, there's data centers and AI, and there's defense. Those are the three large verticals that we go after. And again, most of this is welding, but that's just where we're starting. It's not where we're going to be ending.
Mm-hmm. We are called Industrial AI. Let's talk a little more about your AI-driven approach when it comes to welding and your robot. Inform myself a little bit. The robot scans the workplace and it creates a 3D model of it. And then the system automatically recognizes the shape and the position of the relevant weld seams area. How do you do that? Can you please go a little bit deeper?
Yeah, so that's exactly what happens. So yeah, we build a custom sensor that lives at the end of the robot. That sensor is taking in 3D data.
Is it a vision sensor? What kind of sensor is that?
Yeah, so that sensor has vision capabilities. So it takes in 3D data, it takes in 2D data, so from cameras. It can also take in sound and a couple additional inputs as well. And we take all of that data and then we pass it basically through our large neural network, our neural network that we call Obsidian 1. This is a model that we've been working on for the past 7 years. It's a model that then once you give it all those inputs and you bound it with saying, here is my WPS or the boundary box of what I need, what I can do on the actual welding side. It then takes all that information and then it creates everything past that. How to weld, where to weld, what parameters to utilize to get the ideal shape. But it's able to do that also with the inputs constantly varying. So one of the biggest issues in welding for the long time has been that there's a lot of variability and you have to be within plus or minus a millimeter. And you have to be able to adjust and adapt your heat based on what variance you have. And so our neural network is able to adjust all of those parameters on anything that it sees. So it could have wild variation, not just in location, but also in gaps and tacks and other things that cause a lot of heat change.
But how do you do that with a model? What kind of model is that?
Yeah, so I mean, the model overall, I mean, the best way to say it would be we kind of do imitation learning to get a policy network. And then we have about 7 years of data that we've collected, and we made a world model out of it. So if you guys know what world models are, they're basically neural simulators. So we've created a neural simulator that represents the physics of welding better than any analytical algorithm on the planet. It's basically because, again, we've got tens of millions of welds where we're actually collecting data looking directly at the weld. We use that data to then create this neural simulator. We use imitation learning to get a first policy, but then we actually refine and fine tune that policy with reinforcement learning in the neural simulator.
Okay, that was my question next.
And then
Okay.
at the end, yeah, we have it's basically just a large, neural network that actually then executes on it. So it can, again, the network inputs can take 3D and 2D and a couple other features, and then it literally outputs essentially, waypoints and trajectories and welding parameters for all of it.
I want to come back to your sensor because you mentioned there's a capability for vision, but also for sound. Why sound?
Yeah, so sound's an interesting metric. It's really powerful in welding. There's a lot of human welders that say...
But it's a little bit underestimated, right?
Oh, it's very underestimated. Yes, correct. Yeah, sounds really interesting. So if you talk to human welders, a lot of them will say that they can tell where to weld based on what they're hearing. And it's not something that a lot of people think about in our space, in the robotic space. A lot of people think, I need a camera, I need a 3D map, I need to very logically build out this entire thing so the system can see it. But no, sound is it's a unique input, but it's an input that's really valuable for understanding not just, potentially where you should weld, but really how you are welding in the moment. And it gives good key insight if we think we are starting to weld inaccurately, if we think we're starting to potentially have a bad weld. It's a really key input.
At this point, we will make a brief comment as Andy's colleague has provided us with further information. Quote, at a high level, Obsidian processes these varied data modalities through a modular architecture that respects their unique structures while enabling unified reasoning. Modality-specific tokenization and pre-processing. Each input type is first converted into a format the model can understand. These are discrete tokens or embeddings that capture essential features. This avoids forcing incompatible data like raw pixels or audio waveforms directly into the backbone. Obsidian can take sound, vision, as well as robot state and welder power supply. Adapter layers for alignment. Once tokenized, each modality passes through a lightweight adapter layer. You can think of these as small neural networks tailored to that input. These adapters bridge the gap between raw modality features and the model's shared representation space. In Obsidian, these layers ensure low latency processing, making it suitable for real-time robotics. Fusion and joint processing. Through these tokenization and adapter steps, all modalities are projected into a common embedding space. The core transformer model then processes them jointly. You mentioned 7 years of training or of data. How was the model trained? Who gave you this large amount of data? Is it scientific data or is it real world application data?
So it's all real world application data. So it's all collected from our systems that are in the field. So we currently collect data from every single robot that's in the field welding every single day.
But who gave you this data? Because from a European perspective, the companies are very skeptical when it comes to sharing data with some AI companies building big models. Who gave you the data?
Yeah, so all of our customers to date have signed that they allow us to collect data at their site every single day. It is data, so why are our customers okay with it? They're okay with it because it's data that's really just critical to our neural network learning. It's not data they're collecting anything proprietary about their product or proprietary about their design or anything that they would be really concerned about, having their competitors understand. It's literally all the data we talked about, 3D, 2D data, looking directly at the puddle, looking at the part, looking at the fit up. That's the data that we collect. And we collect it basically at our customer site every day while we're welding.
Mm-hmm. And I want to come back to the process when it comes to welding, because I already mentioned 3D model, then the system automatically recognizes shape, etc., etc. How do you achieve then real-time adaptation to this?
Yeah, so when we are welding, so we do an initial scan, we take that information, we put it through our network, we get our outward trajectories and our welding parameters. Then actually, while we were welding, we turn our cameras back on. And that's really where the sound is utilized. So sound is actually utilized purely on real-time execution, not on initial execution. We are then using, again, cameras, lasers, sound in real-time execution to make adjustments on the fly. And that's about like a 30 hertz update frequency.
Wow. How do you handle that? Is it handled by an industrial PC or by an edge device or GPU, or what kind of hardware do the customer need?
Yeah, so it's definitely an industrial PC. The PC lives with the system, like our cells, and it's about a stack of, depending on how many arms we're running, it's a stack of about 2 to 4 GPUs that basically really power this, so that we can do edge computing.
Mm-hmm. But when it comes to welding, there are different materials. So how do you generalize the model to different materials at the end?
It's a good question. It definitely is one of the harder problems by far, is to be able to get to like a true normalization across the board, so that you can kind of go through, 4 5 wire, 5 2 wire on steel, stainless, etc. So yeah, I mean, it is really kind of one of the more difficult pieces to really get to a single general network that works across all of the materials. So for us, not only can we, one of the ways that we obviously do it if necessary is through fine tuning. So, and, potentially taking the network and then fine tuning on a customer's material. And we have what we call as a data farm. So we have customer data that we collect at the field, basically every day. But then we also do data farm collection basically at our site on our customer's material to allow us to get an initial seed set of data to be able to either validate or fine tune the network from there.
So the fine tuning code is your secret sauce at the end?
Yeah, I would say that, but also just building and collecting all of this data. It's been a journey, and it's really, I mean, it's one of the most critical pieces is how do you get data at quantity, and then truly how do you have the right data to actually have something be functional. I mean, there's not a lot of people in the world. There's probably very few companies truly in the world that are using reinforcement learning to get a output policy network to drive an overall robot trajectory. So but then yes, like being able to move from material, that is also like a critical piece of how to accelerate and really make this be something that can go live versus pure imitation learning and fine tuning on a per customer basis is still like in its infancy and hasn't really been able to be figured out how to be scaled to actual customers yet.
Absolutely. And when it comes to materials, that's one thing. And the next step is now different robots. But I think that's not the big problem, right? So you can work with any robot in the market, or how do you handle this?
Yeah, so we're robot agnostic. There's 2 robot brands that we mainly deploy, which is Yaskawa and Universal. But there isn't a limitation for us. We've got great partners in the 2 of those companies, and we haven't really found a reason why we need to change. But yeah, the stack overall is essentially agnostic. There's a driver that we create that connects to the robot package, and we can do that for ABB and KUKA and FANUC as well if needed.
Okay. Your main focus is the model, or are you building an operating system at the end for welding robots? What is your goal?
The main focus is the model.
Okay. So you want to sell the model then to the Yaskawa guys as a part of their operating system, or is it sold to welding customers of Yaskawa? So what is the business model behind that?
Yeah, so the core technology that we build is really on the model side, or models, right? It's the sensor and the model together. So it's the perception and model. That's really the core technology that gives the large differentiation. The actual business model, though, is robots as a service. So even though those are the 2 pieces that really give core differentiation in the product for our customer, we still have an operating system that we are building for robotics called Path OS. Essentially,
Okay.
it's our
Oh, that's the operating system. Okay.
that really powers the entire system so that we can give our customers still turnkey products. And so we do full stack essentially today. But if you really think about like what we want to build long term, that's the key differentiating element. It's the perception and model at the end.
At the end, the success of a model depends on how reliable the model is. What about the reliability of the model? How accurate is the model? How robust is the model?
Yeah, it kind of, again, in any situation, it's as robust as the data you have to some extent. So again, it's taken us a while. So like, this hasn't been a year of data collection. We've been really doing it for about 7 years, really trying to get the data to we need and continuing to expand the bounds of the data so that we have, most things that we'd see in real life would be within our data set or something close. But the big difference here for us as well is when we move to the world model and we use our current data to create the world model, and then we use reinforcement learning inside the world model, it allows us to get to a finer, it allows us to kind of get to, kind of not necessarily edge cases that are out of distribution, but allows you to smooth the entire network response to be more densely packed inside your distribution. Which has really helped on the reliability side, really helped on the consistency side, I would say. So right now, how we define the overall system utility would be by first pass yield. That's the end piece, right? Is like not just how does the model respond, but then how does the model respond to the entire stack? And then what's the end output for our customers? So the way we look at it is we're about at 98% first pass yield. So about 98% of the time, there is no failure at all, no little failure. It is 100% pass on the weld. And that's with heavy deposition structural welding. So that's kind of how we grade the overall process and the progress. And the goal for us is obviously to keep going from 98 to 99 to 99.5, 99.9, et cetera, et cetera, et cetera. That's really kind of how we look at the consistency of it.
Let's think about a customer, mid-size company, and he wants or she wants to deploy now the model to his or her welding solution. How difficult is it to run the model at the end?
So nobody can run the model at the end. So we only give turnkey solutions today.
Okay. Is it not an option to sell the model by itself?
No, we do not sell the model by itself. No, it's robots as a service. You have to buy the welding robot from.
Okay. So, but it's not an option to do that, to sell the model.
Yeah, it's correct. It's not an option to do that today.
So it's a combination of hardware and the model at the end you sell.
Yep, exactly. Yeah, we sell the whole thing.
Okay, that's great. Where are your markets? Now, we are based in Europe. We are from Germany. Siemens is our partner. And it's funny because we got a lot of interest from US companies to talk to us. And we have the same situation that all our German or European companies want to get into touch with US podcasts or US media because they see that the new big market is establishing in the US. Where are your markets?
Yeah, so we're currently delivered in all of North America. So we're in Canada, we're in the US, and we're in Mexico. And again, the three kind of big ones for us, and maybe fourth, energy, infrastructure, AI data centers, defense, and then, of course, kind of automotive and transportation. So those are the four big verticals, and we're currently in all of North America. Most likely for us next, we will be looking to expand globally, looking at it more intensely and specifically in 2026. We're looking at Japan and Asia, as well as we're looking at starting in Germany and Europe.
Oh, that's interesting because defense is a growing market in Germany in the moment. So everybody's focusing on defense in the moment.
Yeah, there's a lot of it. The big spotlight going on in defense feels like in Germany, in the US, and a lot of other places right now. So yeah, there's a lot of opportunity in that space.
What about competition? What sets you apart from competitors in the welding market with welding robots? You have ABB, turnkey solution for welding. What sets you apart? Is it only the AI or what is your unique selling point at the end?
Yeah, the big unique selling point at the end is the adaptability. So welding robots have been around for 50 years. And I'm at a trade show right now and it's a sea of welding robots. There's probably 1,000 companies here with welding robots. But when you really look at the utilization and the adoption rate for robots, especially welding robots over 50 years, it's pretty low still. Really, it's only been about 20% market penetration over 50 years. And the reason isn't because the hardware doesn't exist or the hardware breaks or it's not robust. The reason has always been that the systems are not intelligent enough to do what the actual human welder does. And they're not able to do it at consistency and speed and reliability. And that's a big, big delta. So for us, we really are the only ones that actually offer true adaptive welding. Welding where it doesn't matter what the fit up is, it doesn't matter what the part is. We can see it and we can understand it and we can make changes to truly weld it. That is really the big differentiation. And again, it goes back to you want to be able to have a robot actually operate like a human welder. Like that's the end state, and that's the goal that a lot of these manufacturers want. They're sold something like that, and then they normally get something very different when they're buying an industrial robot from any of the groups. We're the only ones really able to give them the here's the robot, put the part in front, hit go, and let it go to work. And that's a huge, huge delta there. And then for us, after doing this on welding, we are expanding past it. And so, right, welding is the heartbeat of the company. It's the core competency of the company. But we are going into different embodiments on the hardware side, as well as we're going to different tasks along the manufacturing process.
You mentioned at the beginning you want to spend the most of the 100 million euros in R&D topics. What is on your tech agenda? Because you have a existing model. Do you need to train a bigger model, a more specialized model? What is the idea?
Yeah, I mean, so we're constantly training. So we're constantly continuing to collect data. Right? We're at 98% first pass yield. We want to get far past that. We want to get to 99.9999. We want to be able to have a single neural network that represents 1,000 or 10,000 years of human experience, basically, and be able to get to that first pass yield that is nearly perfect. So that's what we're going to continue to push on in welding is expanding data, continuing to refine how we're training our neural network, continuing to refine and try different practices and try different models to try to continue to increase and improve the overall output. So we're always going to invest in that. That will be an always and forever thing that we invest in to keep moving that. But where the other money is going into is then, again, like the two axes that you can think about is embodiments. So different ways that we embody the intelligence in robots, and then other tasks. So welding is just one task done in manufacturing. The next big task that we're going after is...
So you're already training a different model when it comes to robotics. Are you working on that?
Yeah. So we have Obsidian for welding. That's our model, our brand for welding. And then, right now we're working on what we call Epsilon, which is our model for dexterous assembly and manipulation.
Oh, that's interesting. How far you are now from publishing or from using this model?
So that's a good question. You're asking all hard questions. Yeah, so that's a really good question. The goal for us is we want to be deployed with this model and with this technology in 2026. And so we're working tirelessly around the clock on it. And again, it's the same paradigm of how we've done welding. Of start with imitation learning. Ideally, if you can, create a world model or potentially just create a higher resolution simulation for really contact rich surface. Like we're doing very contact rich, fine grain manipulation work, and then use reinforcement learning inside of that to really get to a global minimum that's actually usable in the real world. So we want to take the exact same paradigm that we've done on welding, and we want to do that on manipulation as well. So that's what we're working towards currently.
Andy, thanks a lot. I keep my fingers crossed for your ambitious plans when it comes to the welding model, when it comes to the Epsilon model. It was fascinating to talk to you. You need to add your head of AI to the podcast because we have one more question, how the model works. And I'm really looking forward to hear more in the next year. Thanks a lot and greetings to the US.
Great. Thank you so much for the time. Very much appreciate it.
Robotik in der Industrie. Der Podcast mit Helmut Schmidt und Robert Weber.